Please welcome Pradeep Vincent.
Good afternoon. Can anyone hear me? All right, cool. All right, so I'm a software architect with the Oracle Infrastructure Service team. I'm primarily a software guy, even though I've learned enough acronyms around networking to pretend like a networking guy, which is why I'm here. So I'm going to talk about some of the architectural aspects around Oracle Infrastructure Service from a network security perspective. All right, so first, network security is a pretty wide topic. It's a pretty old topic as well. There are lots of technologies, lots of products around that. So how is the network security unique in public cloud environment? There are a couple of aspects I would highlight about public cloud. This is not specific to networking per se, but it has impact on how we think about network security. Those two are multi-tenancy and shared control. So multi-tenancy. So elasticity is a key advantage of public cloud, right? So when you go to any cloud provider, Oracle, AWS, or Azure, you essentially pay for the network bandwidth they use, or if you use object store, you just pay for the object store you use. You don't really have to tell them ahead of time how much you need. It's all taken care of. The reason they're able to do that, and the reason we are able to do that, is because there are many customers that are in the same network, and the peaks and troughs of different customers essentially cancel each other. So it's pretty important. But elasticity also means that we need multi-tenancy, right? Just like elasticity, operations is another key aspect of public cloud. In my view, there's a lot of things around the features and the cost model, the pricing model. But in my view, operations is absolutely a big value add that public cloud brings to the table. But at the same time, operations also mean that we need shared control. So if you look at a public cloud environment, you have customers essentially have control over virtual machines, let's say, but the cloud provider essentially has control over most of the network and maybe the internal systems. So there's some level of shared control. Now, the multi-tenancy and shared control essentially bring out a bunch of security risks. Some of them are real, some of them perceived, but yet they both are really important for us to take care of. Now, like I said, these two aspects are not specific to network. It has implications on storage in terms of identity, encryption, so on and so forth. But from a networking perspective, what does it mean? So there are a couple of key implications of multi-tenancy and shared control. First one is essentially the risk of packet misdelivery is really high. So if it's one thing, let's say there's a customer, there's an accounts department or HR department. It's one thing to misdeliver a packet distant to accounts department, to the HR department, but it's a completely different thing to take that packet and deliver it to another accounts department that belongs to a competitor. That's a very different thing, right? So the impact of a packet misdelivery, for example, is pretty high. And in addition, when there's multi-tenancy, there's always a risk of somebody else, an attacker, essentially taking over some of the internal systems, including network devices, and then essentially launching side attacks on a particular customer. So that risk is always there. And the shared control also means that customers need to worry about what can the operators do. The public cloud providers, operators, what can they do? Can they actually peek into my memory? Are some of the big concerns from a networking perspective that customers are concerned about. So what do we do about it? So I'm essentially going to share some of the, looks like I forwarded too much. So I'm essentially going to share some of the key aspects of how we did it. A couple of years back, we started an effort to start a brand new IS infrastructure service architecture. And one of the things we wanted to do was essentially step back and identify the critical areas that enterprise customers care about and incorporate them pretty deep into their architecture. Because sometimes it's much easier to do it early on than later in the later stages. So this is a typical, virtualized data center network. So you have, the black boxes are customer virtual machines. Those virtual machines, the virtual machines are in customer's control. And then you have a whole bunch of blue stuff. There's a hypervisor, the cloud provider's internal systems, and the physical network itself. They're all under cloud provider's control. And then there's a layer of defense. There's the isolation mechanism. Typically, it's a hypervisor-based separation mechanism. And typically, the hypervisor also, somewhere along that, there's a network virtualization layer as well that's added in. So one of the key things we wanted to do better is essentially take a very deep defense in depth posture. Now, defense in depth is pretty popular, but what I'm going to talk about is specific approaches on how we tackle this. This is by no means the only approach. This is just an example of how we tackled it. So in the data center network, we essentially took a three-prong approach, right? So we wanted to have three levels of clear defenses. First thing, we wanted to look at the network virtualization layer and wanted to figure out how we can narrow this down as much as possible, right? The idea here is that when you have a narrow interface, it's much harder for an attacker to get into the internal system, right? Now, the second level of defense is, well, even in the case of a narrow interface, what else can they do? Let's say they actually break out, right? Let's assume that there's some magical way by which they are able to break out. What else can they do? So we wanted to have further defense as well. So the second level of defense that we wanted to architect was essentially multiple routing decisions in the data path, right? What this means is that there are, particularly for critical data path, the security-sensitive data path, we essentially have two different independent devices making pretty much the same routing decision before a packet is delivered. The third one is essentially more foundational in our data center, where we essentially identify pretty much every Ethernet port and categorize them into different trust zones, if you will, and have specific policies around network access across them. All right, so let's take a closer look at these. So this is essentially a representation of what we do. This is similar to a virtualized environment, but it's actually very subtly different. So one of the product goals that we had was, in addition to virtual machines, we also wanted to offer full bare metal instance to the customers. There's a variety of reasons for that. The customers want to run native hardware, bare metal hardware. They wanted lower latency, so on and so forth. So there's a variety of product reasons why we wanted to do that. But in order to do that, we couldn't run any hypervisor, right? So that essentially forced us to think about different ways to do network virtualization. So one of the things we did, we essentially took two components, virtualization device and ILAM. ILAM is used for power on, power off of a server. We essentially took those and logically separated that from the server itself. And we came up with a model where we can give the entire bare metal server to the customer. Now, this also forces us to think about the virtualization device very differently. And very fortunately, in fact, the interface between the bare metal server and the virtualization device now is just a Ethernet interface. It's just a bunch of packets. That's it. So it's much narrower. It has two implications. The narrow interface essentially means it's much harder for an attacker to get in. Two, if somebody who's in the physical network, it's much harder to poke into the customer's server and look at the memory, as an example. So this is essentially what we do for VMs. It's not terribly different than, from a software stack perspective, it's not terribly different than what a typical virtualized environment would look like. But from a security standpoint, it's actually quite different. So what we did was we essentially took the bare metal security constructs and simply used that for virtual machines as well. So here you see the virtualization device is where it is. The top two, the hypervisor and the customer's VM, run as if it's a bare metal, right? So the customer's VM are in customer's control. Those are in the black boxes. But the gray box, the hypervisor, it's managed by us, but at the same time, it's not in the same trust zone as the virtualization device. What that means is that now if a customer's VM essentially finds a way to punch through the hypervisor barrier and gets hold of the hypervisor, they will still find themselves in a bare metal box, and they won't be able to get out. Right? So they still have some attack vector, so they can essentially poke into the other customer's VM that happens to be in the same box, but that's essentially what they can do. So what this does is essentially has multiple layers of defense, particularly in the VM scenario. All right, so clearly the narrow interface helps in terms of improving our security posture. But we wanted to go further. And we particularly for customer traffic, we essentially wanted to take it even further because it's a security-sensitive data path. So this is an example scenario. So we have, customer on the left side, you have two customers' bare metal instances, and on the right side, we have an attacker's bare metal instance. And let's say this attacker's bare metal instance is trying to send a packet to the customer's bare metal instance, even though it's not supposed to. Typically, what happens is the virtualization device that's at the source side essentially figures out, hey, I'm not supposed to route this packet to this destination. So it essentially drops it. It's pretty normal. Most networking gear does this. But what we did was we also had pretty much the same routing decision on the target virtualization device as well. So there are two literally pretty much the same routing decision that essentially enforce the same policy. And let's say in this case, it is an unlikely event that the source virtualization device is compromised for any reason at all. The destination virtualization device will still cache those and drop the packets and create alarms for us so that we can investigate what's going on. All right, so we have a narrow interface, and we have multiple routing decisions in order to add defensive depth. The third one was more foundational. So what we did was we essentially took all the types of Ethernet ports that are connecting to our network, and this is literally an entire physical network, not just the ones that are connected to compute. This includes our internal systems as well. So here on the left side you have a hypervisor, and then you have a virtualization device, you have ILAM, and then on the right side cloud providers' internal systems. And we essentially categorize them based on the trust level. Typically, the rightmost one is the most trusted, and then the left ones are the ones that have a higher risk because they're closer to the compute instance. So there's a much higher chance of an attack. So what we did was essentially, carve these out, and then we created a bunch of network access policies based on our security requirements. This is some of the examples of security policies that we enforce. So essentially, inside the network virtualization trust zone, they can only access each other at a particular port or an IP address or a protocol. The ILAMs, as an example, can't access each other at all. It's mostly because they have no reason to. And from any of the higher risk trust zones, when you talk to the internal systems, there's a whole bunch of severe restrictions. They can only access certain ports, they can only access certain protocols and IP range and all that. Now, you may ask, hey, isn't this just a bunch of firewall rules? Well, it is in some ways, but this is more foundational in the sense that we literally wanted to do this across our network, physical network. And for performance reasons, we have a non-blocking network, and we can talk about that in a separate conversation as to why that's important. Most cloud providers have this by now. Now, the non-blocking network usually means you need to go with commodity silicon for routing, right? And when you go with commodity silicon for routing, there's a whole bunch of restrictions and limitations on those devices as to what type of ACLs and firewalls support. And when you have firewalls or ACL policies that keeps changing all the time, usually at scale, that results in a disaster. So one of the things that turned out to be important was essentially pre-planning our data center layout, which essentially allowed us to do this at a very foundational level. All right, so to summarize, so essentially public cloud brings a whole bunch of challenges. Multi-tenancy and shared control are the key sources of it. They are absolutely the advantages of public cloud, but they also bring in a whole bunch of security challenges. And I think in order to address them, we really need to think about it from a ground-up architecture perspective. It's certainly possible to address them later on as well, but it's generally harder once you have a massive fleet. And some of the examples of how we address that were narrow interface for the virtualization layer, multiple routing decisions on the critical or security-sensitive data path, and having foundational trust zones in our network, physical network, so that the risk is mitigated there as well. Now, there's one last thought I wanted to leave you guys with. I think encryption. Encryption, I think, is going to be more and more important, particularly in the context of public cloud. We do a lot of encryption. Any traffic goes out of the data center, it's encrypted, and so on and so forth. But the reality is that you can't solve this with software if you wanted to encrypt all network traffic, right? And I think at some point in the future, we will get to a point where most cloud providers, particularly the large ones, will strive towards encrypting everything. And if the hardware technology for encryption has been coming along very well, but at the same time, the bandwidth, per host bandwidth, and the substrate network bandwidth has been growing by leaps and bounds as well. And it's not quite catching up. Even in the hardware roadmap of many manufacturers, hardware designers, it's not quite catching up. So if you're a hardware hardware designer working on devices for targeting a public cloud, this is something you may want to keep in mind. I think that's it. Thank you.